In this video, I'll be introducing the horizontal composition of natural transformations and the beginning intuition behind two categories. In the last video, we started off with composition vertically. So we had two categories, A and B, and we had three functors between them. And the composition we defined was for natural transformations, which instead of writing with a single line, I'm going to write with a double line between the functors. So we had a natural transformation there, and we had a natural transformation there. And we could compose those. So if this is tau, and this is tau prime, we define tau prime dot tau at a point to be tau prime at that point composed tau at that point. And that's really basic. That's a really easy way to define composition vertically. Now, what about horizontal composition? So let's be a little bit more descriptive with this diagram. We'll have three objects, A, B, and C, and we'll have Now, what I can do is create a composition. So I'll skip over the category B, and I'll compose the functors. So I'll have F prime F on the top, G prime G on the bottom, and I'll have a natural transformation between them, which I'll call tau prime composed tau. Now this is arrow composition, unlike this dot composition. And the reason why we have the arrow composition here is because you actually compose the functors that you're going between. Now, how can we define this? Well, the way we can define it is by creating a diagram, and you'll see what I mean. So we can start off with F prime F, and we can apply that to a single object A. Now, I'll write this out explicitly, so it's F prime apply to F of A. Now what I can do is I can convert F prime into G prime using, well, this natural transformation, tau prime. So I have to do tau prime, but how would I convert it while keeping this F of A on the inside? Well, I do tau prime at F of A. So this is the morphism. It'll convert F prime to G prime, and the input stays the same. So I remain with an F of A. And then, using tau, the normal tau, not tau prime, using tau, I can convert F to G. So I can have G prime of G of A. But how would I do that? Well, the way I do it is I'd have to keep the G prime the same. So I do G prime, but now I want to convert the inside of the G prime to what I want it to be. So I can do G prime of tau at A, because tau at A will convert F to G and keeps the input A the same. And then the G prime on the outside just keeps the outside the same. All right, now what if I were to do this in reverse? So first, instead of converting the outside, I'd convert the inside. Well, for that, I'd need to use tau, because that converts from F to G. So I want F prime of G of A. And the way to do that is by doing, well, I want to keep the outside the same, so I do F prime, and I apply that to convert the F to a G, keep A the same, so I do tau at A. So F prime apply to tau A. And then I have to convert the outside to G prime. So right here, I'd need to use tau prime to convert F prime to G prime. So I'd have tau prime. And I want to keep G of A the same. So I do tau prime at G of A. So this is the diagram, And you can show, using properties of natural transformations and functors, that it is commutative. Now, the way we define the horizontal composition, remember, we want it to be from f prime f to g prime g. Well, right there, I have something which is from f prime f to g prime g, because remember, I can rewrite this as g prime g applied to a and f prime f applied to a. Now, that diagonal can be defined in two different ways, which is the reason for me drawing out this insane diagram. So we define tau prime, horizontally composed tau, at a point A, and it's going to be either we do tau prime f of A first, then we do g prime at tau A, so that's the first definition, or equivalently, by the fact this commutes, we could also do f prime applied to tau A first, then do tau prime at g of A. So these are the same definition, it's just you might want to use one instead of the other in certain cases. Now, this definition does not necessarily require that it would be a natural transformation. I'm just going to leave it up to you to prove that this horizontal composition is a natural transformation. It's not hard at all. Let's go ahead and compare the original vertical composition with this horizontal composition. So let's say I'm going to draw the diagram right here. So I have three categories, A, B, and C, and we'll have three functors between each of them, like this. Then I'll call one F, one G, one H, between A and B, one F prime, one G prime, and one H prime between B and C. And then we'll have natural transformations between each of these, like this. So this first one I'll call tau, the next one I'll call sigma, and then on this side I'll call it tau prime and sigma prime. Sorry for writing it so small, but I'll always point at where they are in the diagram. So now there's two different ways we can compose these. So the first way is by first doing vertical composition. So first I could do, say, sigma composed tau, right? Because that will take you from F to G with tau, and then G to H with sigma. And then I could also do sigma prime with tau prime by that same logic. So these are the two vertical compositions. So when I do this, what will I get? Well, I'll still have the categories A, B, and C, but then I compose these vertically. So I'll have our functor F, our functor G, and then right here I'll have the natural transformation. Sorry, this is actually H via the vertical composition. And then I'll also have F prime and H prime here. And right there we'll have our other natural transformation. If you look at this diagram, it looks very similar to this one. So what we can do here is horizontally compose these two natural transformations. So right here, I can compose these two horizontally, like that. So what will this get out the other end? This will give us, well, it's going to be from A to C. Then on the top, we're going to have F prime F, the composition, and then we're going to have H prime H on the bottom, and then a natural transformation between them. All right, the other way we can compose these two is by doing horizontal composition first. So I could do tau prime with tau first. So I could do tau prime horizontally composed with tau, as those match this diagram. And then I could also do sigma prime horizontally composed sigma. All right, what diagram does this give us out the other end? well, we're going to have, because we compose this horizontally, we skip over B, so we just have A to C, but we keep 3 functors between them. And we just have natural transformations that go between them like this. So this one on the top is F prime F, this one's G prime G, and this one's H prime H. Ah, look at that diagram. It looks just like this one. So what we can do is vertically compose these natural transformations. So I can go ahead and put a dot between them. And what do we get out the other end? Well, we combine those two, we get rid of the G prime G, and we get this diagram again. So this one will collapse to that one, and this one will collapse to that one. The question is, are these two compositions the same thing? And the answer is yes, they are the same thing, and I'm going to prove that for you, even though it will take quite a long time, but I'll try to explain it the best I can. So the method for proving that these are equal is by looking at their component morphisms. So we can have sigma prime dot tau prime composed sigma dot tau, and we can do this at a general object A. Looking at the diagram we have for this one, which is this right here, and the definition we have for the components, let's just plug in. So we do G prime, so if we look at the diagram, G prime is the lower one. So in this diagram, it's H prime. So we do H prime. What do we apply it to? Well, we apply it to, you can see tau here is right there. So we apply it to sigma dot tau, the first one in the composition. And what do we do it at? We do it at A. All right, then we can compose that with tau prime, which is the second one in the composition, is then sigma prime dot tau prime. And that's going to be at F of A, which in the diagram you can see is still F of A. All right, now we can use the definition of this vertical composition. So we have H prime, and we do it at, well, right there. It's sigma at A composed tau at A. Then compose that with, right there is sigma prime at F of A composed tau prime at F of A. All right, I'm going to simplify this more later once I have more information. Now looking at this one and this diagram, let's use the definition of vertical composition to find its first component. So first we have sigma prime composed sigma dot tau prime composed tau, and we do it at A. What do I get? Well, I get sigma prime composed sigma, and this is horizontal composition, at A composed tau prime composed tau at A. This is morphism composition. Please note that. So let's go ahead and just plug these into the definition again. So for this first one, what do we get out? Well, G prime in this case is H prime, so I do H prime, and I apply that to, well, that's the first one, sigma, at the point A, and I compose that with, well, this one's going to be tau prime, which is sigma prime, at F of A, which is really G of A. And then I compose that with, now let's go ahead and do the same thing with this one. So I do G prime of tau at A composed tau prime at F of A. All right. Now you can already see some similarities in that we have sigma A right there and right there, and we have tau prime at F of A right there. The only difference are these two in the middle. So let's single these two out. Let's see if I can flip these two using a diagram. So let's go ahead and draw out a diagram using these ideas. So I can go from tau to sigma, and then I can go from sigma to sigma prime. So, at a point, now what point do I want it to be at? Well, probably A, because it makes sense right there, tau A. And I can go across with tau A to G of A. And then, if I apply G to both sides, I can get G of F of A. And then, sorry, it should be G prime. And then I can get G prime tau of A right there in the middle. And then G prime G of A. Then, from G prime G of A, I can take sigma prime at G of A down to, it converts the outside to H prime at G of A. Guess what? This is the same idea we had with this one, so I can take a different path. So right here, I converted the inside, then I converted the outside. Let's do it the other way around. So I convert the outside to H prime first, so G prime to H prime is sigma prime first. So I do sigma prime at what point? Well, I want to keep f of a the same, so sigma prime at f of a. All right, then this will take you to G. So this will take you to H prime of f of a. Then I have to convert the inside next. So I do H prime, because I want to keep that the same. And I apply that to, well, f to G is tau. And at what point? Well, A is in both of them, so it's tau at A. And so I can convert this right here in the middle using this diagram. We have H prime sigma of A composed. What's this going to be converted to? So that composed that is the same as that composed that, and you can prove that using properties. So the first thing we do in this path is we do sigma prime at f of A. Then we do H prime at tau of A. So I do composed H prime at tau A. All right, then I compose this with, well, what's left? Tau prime at f of A. Guess what? If I erase some of this stuff so I can write it down, if I can find my eraser, let me write it out better. So this is what we were left with that diagram. As you can see, this composition right here, because it's a functor, functors preserve composition, I get H prime applied to sigma A, composed tau A, and then composed sigma prime f of A, composed tau prime f of A. And as you can see, this right here was the result from the first composition. This is the result from the second composition. They are the same thing. Therefore, we have this interchange rule. So, as you can see, we can interchange vertical and horizontal composition in such a nice way. Now, a way of looking at this always helps me remember, is I can view this dot as a functor. So it'll take in sigma prime, tau prime for this one, and composed, this applied to sigma tau. What do I get out the other end? By this fact, that's this applied to sigma prime composed sigma, tau prime composed tau. So really, under this as the composition, you can view the vertical composition as a functor. So this interchange rule really shows them as functors on each other. So this is nice and all, but what exactly can we do with this interchange law? What are the nice properties that can come with this interchange law? What this law allows us to do is create what's known as a two-category. So the idea behind a two-category is basically the idea of cat. So a two-category is like a generalization of the category of categories, in that we have objects like A and B and C, and we have arrows between them, which are functors. and then we can have natural transformations between them, like this. Now the thing about the end, we have two types of composition. We have horizontal composition and we have vertical composition. Notice that in this diagram, nothing really represents anything concretely like I've been discussing here. So what a two category is, we have objects, we have morphisms, which are these arrows, and we have what are known as two morphisms. Now what two morphisms are, they are morphisms between the morphisms, like natural transformations. So right there is a two morphism in the example of the category of categories. Now the property we have to have is that it has two different compositions. One composition is this vertical composition. This is the one we explicitly have to define in a two category. So first of all, we have the operation dot between two morphisms. So in the category of categories, this is vertical composition of natural transformations. This right here is just some composition between two morphisms. So we have the dot operation, and we also have the composition operation, and they have to have the interchange rule. So if we have these two operations, they can be interchanged in this way. We have a two category. Except we also have to have a little bit more structure on these with what's known as uniters and associators, but that will come up when we talk about monoidal categories. So right now, just think of a two category as a generalization of having natural transformations between functors and the vertical and horizontal composition. You can see that this interchange rule really is the thing that defines two categories, and that's why it's useful. And that's it! And that's it! And that's it! Okay, I needed to get multiple recordings of that for some reason.